Hi, I'd like to take a moment to explain a very popular implementation of a binary search tree in Java. It is a particular strain of the tree data structure, where notably each parent in the tree essentially just has or is limited to two children. Nonetheless, we have an overarching tree class here, and to actually get the class started, we mentioned that the tree data structure consists of nodes, and therefore we have a little class, which is a node class, an implementive detail which builds out the node. Each node is actually going to have a left and right reference, so it's going to reference a node to the left of it and a node to the right of it, which makes having a left and right reference necessary. And each node will consist of data, and a constructor will tie this data to the node. These are different types of traversals that we'll certainly discuss, but for the most part, this is our main concern here, which is sort of the create tree method. What is essentially happening is when we run this class, we're entering, we're receiving data. So let's say I entered 2. Now, as I enter 2, now it's letting me populate data to the left of it. So I can enter in a number like 4, and then again it asks me for data to the left of it, and then suppose I entered 7, and then again it asks me data to the left of it. Suppose I entered 6. And what would essentially be happening here, and this will sort of be demonstrated on the board. What's essentially happening here is I have a tree like this, and I'm just I'm basically just constantly populating half of this tree, sort of, where it's just asking me, okay, it registers the node, it registers the node, and then it basically says, okay, well, what do you want to the left? And then again it asks me, what do you want to the left? And then it keeps doing that. And what it's now going to do is it's now going to work its way back up and be like, okay, what do you want to the right of this? And then what do you want to the right of this? And so on and so forth. And then it's going to do that on an individual basis. But for the main first part of this build, what's going to happen is it's just going to keep moving to the left, and it's going to say, okay, well, what's to the left? What's to the left? What's to the left? And then it'll work its way back up, and we'll see it doing that. The motivation is to sort of have a tree, that looks something like this here. So we have, something like this, and this is an instance of a binary tree. Let's see. Where each has so not every not every node has to have 2 children. Like one in this case actually doesn't have 2 children, but they're limited to 2 children, right? So I could have something here, but now I can't branch off of this and then make another one. That would not actually be a proper binary tree. But nonetheless, that's the motivation, and we'll actually see how this program does that. So now that we're back to the IDE here, as you can see, it's asking me for the left and whatnot. If I enter in -1, then it knows that I don't want to have, I don't want this node to have a left. And then so now it asks me for the right. And, let's say I entered in a value for the right, and then it treats this node now, okay, this new node, which is to the right, can have a left. It can also have a right, right? That's why I said it's treating this on an independent basis. So I could enter in 9, and then it will ask me, it will keep doing that process, except for, just what we described, keep building on the left, right? If I enter -1, it'll then ask me for the right, and then so on and so forth. And then it'll build this tree that way. And then ultimately what's going to happen is we're going to reach the actual root, and then it will do the same thing with the right side. So, let's go ahead and actually, move to the whiteboard and see how these recursive calls are taking place. Because, recursive calls are difficult to visualize even for me. So, I tend to do something like this here. So, firstly, we create a tree. So we trigger a call to this function create tree. It creates a node, which is, null for the time being. Then it asks you to enter in the data, and then the scanner facilitates that process. So let's suppose we entered in, 2, right? We entered in 2 here. And then it checks, is that data equal to -1? It's not. So then it instantiates the root, and then it asks for what should be to the left of 2. And then the root, this is an independent root we're talking about here, a unique root, and its dot left property that is being accessed from the root class. Its dot left property is actually set to a recursive call. It's set to the same method. So you actually stop executing from here. And what happens is you call another, it's kind of like you add another one of these calls onto the stack. And so now you're coming inside this method. You're like, okay, now you create it. So this actually doesn't know what its left is. Not right now. But it then triggers a call to the create tree again. So it's going to, almost like a loop, it's going to start from the beginning, right? And so it creates so what do we have in terms of, in terms of the tree structure? We did create that 2 there, right? We created that 2. And, it's an established node. And then now it's asking for the dot left. So over here, node root is equal to null. It's asking you to enter in the data. So that gets printed to the screen. And then suppose you entered in 4, right? Suppose you entered in 4, or actually that looks like a 1, but suppose you entered in 4. Is that data -1? It's not. So we instantiate a root. So we come back up here, we make a new node, and that data is actually passed into the constructor. So it gets registered as the data that's associated with that node. And then it's asking you to enter in, what's the left of this now? Again, that was the motivation, was just to continue populating the left. So it says, okay, well, what's the left for this? And then it says, okay, this 4's.left property will be set to the recursive call create tree. And then we stop from here. And then, we come back and we make another function, right? Or we trigger another function call. It creates a root. And now it asks you to enter the data. The scanner facilitates that. Suppose we entered in 7. Is that data -1? It's not. So we'll actually put an X mark here. It creates the root, takes in data. So then you successfully have, 7 as another member here. And then it's asking you to enter in left, right? So, can you enter the left value, right? And then again, 7's root.left is set to another recursive call, right? And here we have another recursive call to this function. So this is us building out the tree here. And as you can see, it creates a new node, asks us to enter in the data, scans it, we'll take in 6. Is that data -1? No, it's not. The root is set to 6, and then asks for what its left will be, and then it creates yet another recursive call. This time we'll enter in -1. So we did enter in 6, but now when we're coming here, we're going to enter -1. So what's going to happen is, is the root equal to null? No, it's not. Enter data, scanner. Is it -1? Yes, it is -1. It returns null. So it actually, this is the important part. It returns null. So, what has happened is when we entered 6, it wanted us to enter in what the left of 6 will be, but we want to actually, stop creating this part of the tree after 6. We don't want 6 to have a value here or a value here. We just want it to be sort of what is called a leaf node. which is sort of a node doesn't have any children. So we actually return null, right? And then this value of null is sent back to this, right? So the six's root dot left gets set to null, okay? And which is what we wanted. Should not have a value, right? And then what happens when root dot left finally gets a value, the execution of this program, of this particular method call, will continue. So you will then move on to this print statement here, and then it will ask you enter in the the data that should be associated with the right value of 6. And then so this is then going to go off to the side. It's going to print this to the console, and then it's going to say root.write create tree. So it will instantiate, it will set this this node's write reference to yet another call. So it's going to go down here, and then it's going to say, okay, well, now you're populating the right of it. It creates the node. It asks you for the data. Suppose we enter in -1 because we don't want any data for the right of 6. And then it says it's -1, so we return null. So this too, it comes back. This too is set to null. This is also set to null. So root.left is null, root.right is null. Both of these are essentially null. And that is what we wanted. We wanted 6 to have a right and left of null. So this actually works out for us. And then it just returns root. Now, what was root? It was 6. 6 was the root. So that 6 is being sent back up. It's being sent back up here to this call. Root.left is 6. Because remember, this frame belongs to 7. And now root.left is 6 for 7. Root.left is 6. So that's exactly what we wanted for 7. It's root.left should be 6. And then after this finally gets a value, when root.left finally gets a value, which is 6, so 7 has a root.left of 6. When it finally gets a value, we then ask, okay, enter in what should be at the right for 7, right? And suppose we don't want anything for the right. Suppose so it asks us for the right, and then root.right is set to another call. And suppose we don't want to set anything, so we say root node root is equal to null, enter in the data, it registers the data. Suppose we say -1, and then it stops right here, right? And then so this is set to null as well. So 7's root.right is also set to null, which is what we wanted based on the tree that we were trying to make. And so now it returns root, which is 7. So what's the implication of that? Well, now this has a value. Root.left finally has a value for what? For 4. So now 4 knows that its root.left is 7. And then after it finally gets that value, as soon as it figures out that its root.left is 7, it then this stack or this frame of the call, then continues its own execution. It says, okay, root.right is equal. So what's root? Now it begins to ask, I know what my left is, what's my right? And so it then triggers another call here. Okay, it triggers another call. Let's try to put this one to like an actual value. So what we're going to do is we're going to say, okay, it knows what its right is. Now it knows what its left is. It then makes a call to the, it'll set right to a call for a create tree. It says node root is equal to null, enters in the data, and data is registered. Suppose we entered 10, it's not -1. And so the root is set to 10. So its right value will actually now be set to 10. And now, so this is now a valid node that has been entered. And for each node, we would ideally want to ask what the left and right is. So it asks, okay, well, enter in the left, right? And suppose we don't want tend to have a left or right. So what's going to happen is, root.left will be called, and we produce another stack or another, recursive call. And we're going to set this to -1. So all of these executions happen. We set to -1, it returns null. So it comes back up here and it says, okay, well, 10 will have a root.left of null. It will then continue its own execution. It will ask you for the right value. It will then trigger another create tree function. And you probably know the rodeo now. I mean, when it asks for another create, for what the right will be, it triggers create tree again. It says node is equal to null. It enters in the data. We enter in -1, and then it returns null. So now root.right is null. So root.left and root.right is now null, just like we intended. And then what is it going to do, right? It's going to return root. It's going to return 10 back to this for frame, right, for 4. So now root.right is set to 10, and then it returns the root. Root gets returned, it's 4. So now 2 finally knows that what its root.left is. It's 4, right? Just as we intended, it's 4. And then it continues the execution of its own program, and then it asks you for what the right will be. And this is where we begin moving to the right of the tree, right? So we've really taken care of the left tree, or the left subtree. We've taken care of this entire area, and now it has began moving to the right of the tree, and it will continue this entire process that we've described, except it will do so for the right of the tree. And so that's the idea. So let's try to hash this out here. So it says, and by the way, it's not going to know, and just as we've described, it's not going to know what its right value is firmly until all these other nodes have solid values, right? Because then it's going to pass up what the value is, right? And then it's going to pass up what the value is. Then 2 will finally know what its root is. And so this entire process is continued on for the right side. And these recursive calls are made independent. So each node is treated as though it must have a left, it must have a right. When we return -1 for both of them, then we start moving back up the tree. And that tree in specific could be either the right or the left, depending on our view.